Okay, so the next speaker is Professor Ulla Vogel from the NRCWE in Denmark, so thanks very much for coming. Ulla is an in vivo toxicologist, if I can call you that, and she's a fantastic talker. I always learn something new from listening to her, so no pressure at all there.
What a start. Thank you so much. And thank you so much for the invitation to come here and speak. I'm really honored by the invitation. I'll talk about particles and cancer, and I'll just introduce the National Research Center for the Working Environment. We are a government research institute under the Ministry of Employment, and we have looked at or had nanosafety and particle toxicology as strategic areas since 2005. So a little later than Vicky, but we were catching up. And we are act as advisors for the Danish Working Environment Authority, for the Danish EPA, sometimes for the EU Commission, the OECD, and WHO. So I'm going to talk about cancer. Cancer is uncontrolled cell division, and you can think that if cancer was a car, then either the speeder would be stuck or the brake would be out of order. Yeah. And cancer is very common. At least in Denmark, 1 in 3 will get a cancer diagnosis before the age of 75. And age is the most important risk of cancer, as you can see here. So increasing your life expectancy will also increase your risk of cancer. Also in Denmark, 2 out of 3 Danes will be closely related to a cancer patient. Major causes of cancer include genetic predisposition, smoking, alcohol, which gives breast cancer, sunlight, meat intake, hormone replacement therapy, also for women, and the working environment. So a number of particles that occur in the working environment have been classified as either as carcinogenic to humans. We all agree that they're carcinogenic, or possibly carcinogenic. They may be carcinogenic by IARC, which is the WHO's research institute on cancer. And I'd like to highlight diesel engine exhaust, high volume materials, black pigment, carbon black, and white pigment, titanium dioxide. And then one specific carbon nanotube that was classified as possibly carcinogenic to humans 25 years after the first description of carbon nanotubes. So when you think about which compounds are carcinogenic, we have the ones that we have agreed upon are carcinogenic, and then we have the ones that we have not yet tested, or maybe the ones that we have not yet agreed upon whether they are carcinogenic or not. And if we look on the global burden of occupational cancers, there was this paper from finding out the global burden of occupational cancers from 2016, concluding that more than 95% of the known occupational cancers are caused by exposure to 4 agents: asbestos, secondhand smoke, quartz, and diesel engine exhaust. The implications are here that if we can limit exposure to these 4 agents, then we can actually prevent a lot of occupational cancers. Of course, the challenge is that some of these occupational cancers have a very long latency. So this is an example of asbestos import in Denmark and asbestos-induced mesothelioma. So the asbestos import peaked in 1970, whereas the mesothelioma had not peaked yet 40 years later. I had another example here with coal mine dust, and now I don't know whether I will get comments on that. But here they found associations between coal mine dust exposure and lung cancer after 37 years of follow-up, but not at earlier time points. So their interpretation was that the lung cancer took much longer to develop than a lot of the other diseases that were related to dust. So prevention of exposure to occupational carcinogens may take decades to show effect, and this calls for due diligence in relation to prevention of exposure to new occupational carcinogens. Much can be gained if we don't need the epidemiological evidence. So I've been involved in regulation trying to set new occupational exposure limits, and I know that what is really preferred is epidemiological evidence, not animal studies, and definitely not in vitro studies. And for the epidemiology, of course, you need the human exposure. Carcinogens share common modes of action, and in this very important paper, 10 hallmarks of cancer have been identified. This was published by members of IARC working groups, and 3 of these characteristics or hallmarks are really relevant for particles, and they are highlighted in red. The first one is being genotoxic, and this can occur if particles release toxic substances, for instance, PAHs or metals. Then the other one is that they induce oxidative stress, as Vicky also highlighted, and a number of particles, especially cold carbon-based particles, will generate surface-dependent radical oxygen species. So a lot of particles will induce large amounts of oxidative stress. The third one is induction of chronic inflammation. The inflammation will depend on or be predicted by the total deposited surface area of the inhaled or particles in the lung, and also shape, as Craig. The fiber shape will also induce a lot of chronic inflammation. So many particles have the potential to be carcinogenic. So I'll just take diesel as an example. And diesel is now a known carcinogen. It was classified as carcinogenic in 2012, so 10 years ago. The emissions contain both the gases and the particles. And the particles, as you know, they are nano-sized particles that often aggregate in air. So maybe they're not detected in the ultrafine fraction, maybe they actually hide in the larger fraction. They have a solid carbon core, and they have associated pHs and organic carbons. They may also have absorbed metals. New generation diesels with lower particle mass have a higher content of metals. They're measured often in terms of PM or elemental carbon. If we look at the mechanism of action, in 2-year cancer studies in rats, diesel exhaust will induce lung cancer, but filtered diesel exhaust will not. So the particulate fraction is the carcinogenic fraction. Both inhalation of the particles and pulmonary exposure to the particles and pulmonary exposure to extracts from particles induce mutations in lungs of mice. And there's evidence that both the carbon core and the diesel particle extracts, which can be the pHs, the organic carbons, contribute to carcinogenicity and henotoxicity. So the mechanisms here point to DNA adduct formation by the PAHs and particle surface-induced ROS, both mechanisms of primary genotoxicity. If we look at human data, epidemiological data, there was this very important meta-analysis performed by epidemiologists who participated in the IARC evaluation of diesel engine exhaust. So they made this meta-analysis where they included all studies that met the criteria that the exposure should be given as cumulative diesel exposure for dose response analysis, that they had an appropriate control group, and that the studies contained no major shortcomings. So the 3 studies here fit on a nice dose response curve, and this is the information that we need or is required for health-based risk estimates. And they also made these health-based risk estimates. And what they show here is that following 40, if you look in the, maybe I can even point. Yeah. If we look at occupational exposure for 45 years to 1 microgram per cubic meter, this is a level close to what you see in a busy Copenhagen street. I don't know how it is now in London after the ultrafine. This exposure would induce 17 excess lung cancers per 10,000, so 2 in 1,000. This is very close to risk estimates that are usually accepted in the Netherlands or in the US. The EU tends to want to have risk estimates at 1 in 10,000, so tenfold lower than this. The high estimate here says that exposure to 25 micrograms per cubic meter would give 7% excess lung cancer. And just the EU recently adopted an OEL for diesel exhaust at 50, so the double of the risk estimate that you see on the high end there. Denmark adopted a five times lower OEL on July 1st last year, and will negotiate in 2020 to see whether we can lower the OEL further. So this is the OEL that the Netherlands also have. There are other insoluble particles that have the same carcinogenic potential as diesel exhaust in inhalation studies in rats. And these are studies from the 90s, showing here dose response curve, where the green ones are diesel exhaust, and the black ones here are carbon nanoparticles, so black pigment particles, and the purple one here is titanium dioxide nanoparticles. So they all fit on the same dose response curve, showing that they have the same carcinogenic potency. And when you compare this potency with the human data, then the rats do not overestimate human risk. Meaning that for this, animal studies can be used for human risk assessment. Animal studies also show that the nanosize really matter for the carcinogenic potency. So here there are studies on white pigment, titanium dioxide, which is micrometer sized or nanometer sized. And for the micrometer sized, it took 250 milligrams per cubic meter for 2 years to induce lung cancer in rats, whereas for the nanosized, it only took 10 milligrams per cubic meter, so 25 times less. Of note, the Danish occupational exposure limit on titanium dioxide is the same 10 milligrams per cubic meter, where 30% of the rats got lung cancer after 2 years exposure. So I just want to conclude here. A large fraction of the global burden of known occupational cancers are caused by a few agents: asbestos, secondhand smoke, quartz, and diesel engine exhaust. So actually, you can do a lot of due diligence by just updating 4 occupational exposure limits so that they really reflect current knowledge. Nano-sized particles may be more potent carcinogens than larger particles with the same chemical composition, and this calls for specific regulation of nano-sized particles. Diesel engine exhaust induces lung cancer at very low exposure levels, and in rat inhalation studies, other insoluble particles have similar carcinogenic potency as diesel exhaust particles. Just going to stop on a little more positive note here, and this is to say that it actually matters to lower occupational exposure limits. They contribute to lowering the actual occupational exposures in the work environment. And this comes from a report from Institute of Occupational Medicine, and maybe even John Cherry is here today. I think, yeah. Yeah. So thank you for your attention.
very much, Ulla. Really great. Thank you very much indeed. Questions, Vicky?
Ulla, you mentioned with the new diesel that the proportion of the particle emissions has higher net.
Yeah.
So has there been any work done to see if that impacts
no, I think there have been studies showing that I think when you look at the particle mass from new engine particles, it has the same potency, toxicity potency. It's just a little different whether you get more inflammation or whether you get more DNA damage. But the emission per vehicle obviously decreases, so the risk associated with each vehicle is decreased. But when you have the pollution, it's all the same.
I've got a bee in my bonnet. The original hypothesis was to explain why such a low dose of particles could cause effect in an organ other than the one which they were deposited. It was based on a very simple idea that the lung responds against bacteria and viruses. Those are the things that count. When it gets a lot of then it responds and causes reaction. It's a very simple idea, and it required a potentiation to explain the possible. But you never measure particles. No one measures particles. I mean, it's the obvious thing which Frank should have been measuring 20 years ago. And you're not measuring. You're giving a great big dose of bigger particles, a tiny dose of small particles, getting bigger response, tiny. But you don't know how many, or do you? How many particles that you're actually giving?
So you can calculate, but I think the problem is especially in ambient air that the tiny particles will aggregate, and a lot of the devices that you use for measuring particles, they will measure mass over charge. So you will not be able to distinguish between a small particle and a large agglomerate with more charges on. We've looked a lot into.
You're looking at surface area.
Yeah.
Surface area is
Yeah. But even unfortunately, you have very few. I have not come across. I'm not a measuring person. I'm a biochemist, but I have not come across devices that can actually solve that. If you can have these agglomerates, how to correctly measure what is actually the surface area in that agglomerate. They tend to look at agglomerate and see a football. And before we can actually solve that problem, I don't think that we can solve the real issue and find the real evidence of the health effects of the ultrafine particles, because they will hide in the larger particle fraction, and this is why a lot of studies fail to find the associations with ultrafine exposure and disease.
The Danish diesel exhaust OEL, is that actually achievable, or is it just drive forward using electric?
So I think that the 10 is actually very achievable. It's and it's associated with a quite high risk, actually. Yeah. So yeah, I think it's very achievable. It's more a problem if you have underground mining or if you have tunnel work or inside engines running.
Great. Thank you very much.
Thank you. I'll just have some extra slides. Okay.